Hello friends, welcome to this channel Dr.ARM's Chemistry. We will discussing the metal carbonyls and related compounds, and in this case we are now going to see the third point. This is the third point of our lecture, that is the 18 electron rules. 18 electron rules. Now this rule states that when the element, that is the atom of an element, that is metal or non-metal, has to arrive at stability, then it has to attain the 18 electron configuration either by loss of electrons or gain of electrons. Means it needs to share or donate or gain few electrons from other species and thereby attain nearest inert gas or next electronic nearest inert gas configuration or noble gas configuration. Then we should know that this is also called effective atomic number, and this number is the number of next inert gas to the concerned metal ion. For example, if we are considering 3D series of transitional metals, then the next metal ion is the krypton with atomic number 36. So we will see some examples in order to study this. For this atomic number, effective atomic number is given by, that is EAN, is given by M plus 2Y. M plus 2Y. So for example, if we take here we are considering the general example of MCOY. So here the metal ion is mononuclear. This complex is mononuclear, and here this M indicates atomic number of metal, and this Y indicates the number of ligands bonded to the metal ion, bonded to metal ion or atom, ion or atom. So this is the case for some simple molecules. For example, if we are having CrCO6 or FeCO5 or NiCO4, so these are various complexes in which we can apply this effective atomic number law. For example, in case of this, the effective atomic number, that is the atomic number of chromium, is 24 plus the number of electrons donated by or shared by the ligands. The number of ligands are 6. So 6 into each ligand donates or shares 2 electrons. So 6 into 2. So this gives us 12, means 24 plus this 12 is equal to 36. And this is what we say effective atomic number. Then in this case, if we consider this Fe, so here these metal ions are existing in the zero oxidation state. So we can have this Fe as scandium, titanium, vanadium, chromium, manganese, iron means it has atomic number 26 plus 5 ligands into 2 gives us the 26 plus 10, that is equal to 36. And now here in case of nickel, the metal ion atomic number scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, that is 28. So 28 plus 4 into 2, so 28 plus 8, that is equal to 36. So here you find that all these complexes are formation of these complexes results in the attaining the next inert gas configuration of krypton in this series, that is krypton with atomic number 36. Then we consider this 18 electron rule for binuclear complexes. For example, that is binuclear complexes. For example, if we take Mn2CO10, Mn2CO10, then this effect, this 18 electron rules means the number of 18 electrons can be calculated like this. So each ligand which is terminally positioned shares or contributes the 2 electrons each. So each or every ligand will contribute 2 ligands, and the bridging ligand will contribute 1 electron. So that will also vary with different examples. Then this Mn or metal ion will contribute the number of valence electrons. So in case of Mn, the valence electrons, so we will show here Mn has valence electrons, that is 7. So scandium, titanium, vanadium, chromium, manganese, so 5 electrons of this are there, means 7 electrons are contributed by these manganese. So terminal, so valence electrons are 7, so 5 electrons from this subshell and 2 electrons from S subshell. So total gives 7 electrons in Mn. Now there are terminal, this carbon monoxide, so which contributes, so we are counting this number 18 electron for only 1 Mn. There are 2 Mns, so we are using here only 1 Mn and half of this carbon monoxide. So there are 5 terminal carbonyls, so each gives total 10 electrons. So these are 10 electrons. So Mn, we will show here valence electrons of Mn 7. 10 electrons are contributed by this terminal CO, and there are 2 Mn, means there is Mn bond which contributes 1 electron. So if we add these, you will get 18 electrons. So this is called 18 electron rule. So we will see this rule for in case of another example. So we will take number of such examples. Then second example is OS, that is osmium, OS2 CO9. Here the osmium has valence electrons. So valence electrons of osmium are 8. Then there are carbon monoxide terminal carbon monoxides. So each will contribute. We are taking here half of this, means 9 electrons are there. So the two O's cannot contribute equally to the carbon monoxides available. So one of these 9 carbonyls is sharing here between 2 as bridging ligand. So terminal ligands are therefore 8 divided by 2 means 4. So these 4 carbonyls groups will add into 2 electrons, that is 8 electrons, and bridging carbon monoxide, that is mu, contributes 1 electron, and there are metal, 2 metals, OS, osmium will contribute 1 electron, and this will give us, that is 8 plus 8, 16 plus 2, 18 electrons. So in this way, this example also follows 18 electron rule. Now we will consider another example, that is so you can see here Re2 CO5, then cyclopentadiene to this cyclopentadiene. So it has a structure like this. Re has this CP cyclopentadiene and these terminals used. This Re, we have this cyclopentadiene. So here this CO, and this cyclopentadiene. Then there is one more carbon monoxide which is shown here as bridging group. So we can calculate the 18 electron rule, the number of electrons like this. So metal ion valence electrons of Re, there are 2 Re, but we are calculating the 18 electron count for only one of them, or means both Re will have same count. So we are considering here only one Re. So it has number of valence electrons 7. Then there are, this is cyclopentadiene. It is eta 5. This cyclopentadiene is eta 5. Means it has 5 points of attachments. So it contributes 5 electrons. So this cyclopentadiene will contribute 5 electrons. Then there are 2 plus 2, only 2. because each already has 2 carbon monoxides. So 2 into 2 is 4. Then 1 2 means 7 plus 5, 12 plus 4, 16, 17, 18. So this is 18. The total of this 18 electron rule. Then we go to the next example. There is another example, that is Fe3CO12. Fe3CO12. And the structure of this is Fe like this. Then there are the bridging CO like this. This is one more CO which is also a bridging CO. Then there are only 2 such bridging groups of CO. Then we will see the terminal. Like this. Then this will have CO like this. So this is the structure of F3CO12. Now we will see that here you will find that each CO contributes to electrons. This CO contributes to electrons. This CO also contributes to electrons. So each iron, this Fe has this CO will contribute 1 electron to this, 1 electron to this. This CO will contribute 1 electron to this and 1 electron to this. So ultimately each CO means there are 2 COs, 2 Fe's. Means 2 Fe's will contribute 2 electrons each from this one electron, and this one will contribute 1 electron. So we can calculate the as a ratio simple in a simple form like this. So each Fe, this for each Fe there are CO4, or each Fe there are 4 COs. So from this we can get the Fe valence electrons of Fe are 8. Then the terminal carbon monoxides, that is 4. So into 2 electrons. So this will give us 8 electrons. Then Fe bond is there. So each Fe will get there are 3 such Fe bonds. So each Fe bond will contribute 2 electrons. Means say this Fe and this Fe. So this will contribute 1 electron. This will contribute 1 electron. So in this way, these two are also contributing 1 electron. So we have taken here 2 electrons in this. And now this total will give us 18 electrons. Then we will consider another example. We can have this example as Re. Here Re is in +1 oxidation state. So Re is having this ligand isopropyl. And this cyclopentadiene with negative charge, one negative charge on this. Then there is carbon monoxide, 1 PF3 and 1 Xe. And now we will show the contribution. Now we can show that this Re will contribute 6 electrons. 6 electrons. This isopropyl cyclopentadiene, which is having 1 negative charge, that is mononegative, will contribute 2 electrons. This carbon monoxide will contribute 2 electrons. This Fe will contribute 2 electrons, and this Xe will contribute 6 electrons. So if we add these, we will get 6 plus 2, 8 plus 2, 10 plus 2, 12 plus 6, 18 electrons. So in this way, we can get this electron count. Here, this donor is specifically having single negative charge. Single negative charge. So we are taking here 2 electrons. This is another example where there are 2 Fe. That is, we can show the formula as Fe2 CO8 and H. So here this Fe is in zero oxidation state. So this Fe in 0 we have valence electrons count, that is 8. Valence electrons are 8, means 6 electrons from D and 2 electrons from S subshell. Then there are 3 terminal COs into 2 electrons, so that is 6. Then there are 2 mu, means bridging carbonyls, carbon monoxides. So they will contribute 1 electron each. So 2 into 1. So that will give us the 2 electrons. Then there is mu H bridging. This is mu H. Mu H bridging. Mu H. So this one mu bridging will contribute 1 electron, and the Fe bond will contribute 1 electron. So here this mu H contributes half electron each. Mu H contributes 1/2 electron each. for this Fe, and there are two such Fes. So every H, bridging H, contributes 1/2 electron. Means the actual electron cannot be divided, but it is mathematically taken as 1/2 contribution per metal ion. So total of this gives 8 plus 6 means 16, 17, 18. So this is one example. Another example we can have is this structure will show us that Fe is bis cyclopentadiene. So here the electron count is like this. So this Fe, valence electron count, shows that Fe contributes 8 electrons. Then cyclopentadiene, there are 2 cyclopentadienes here. So 2 Cp, therefore each Cp contributes 5 electrons. So there are 5 carbons. So each carbon will contribute 1 electron. So 2 Cp means 2 into 5, that is 10 electrons. So it gives 18 electrons stream. Another example is eta 6 C6H6. And this is here chromium is in zero oxidation state, carbon monoxide. The structure is like this, and we can have the electron count like this. Chromium in zero oxidation state will contribute 6 electrons. Chromium in zero oxidation state will contribute 6 electrons. Then there are these 3 terminal COs which contribute 2 to 3, that is 6 electrons. Then this eta 6 C6H6 will contribute 6 electrons. So this will give us the total of 18 electrons. So in this way, here we will find that the 18 electron rule is also obeyed. Then next example is important example, that is RH. We have this CO, then Cl, RH, like this, CO. So here, this Cl, this RHCl, means this Cl contributes 1 electron. This Cl contributes 2 electrons. So here this Cl contributes 1 electron. This Cl contributes here 2 electrons. And each of these will contribute 2 electrons. Now we will show the electron count like this. RH, valence electrons, are 9. Then first problem we will take 2 carbon monoxide per RH. 2 carbon monoxide, that is terminal, will contribute 4 electrons. Then each RH will be in contact with 2 Cls. This RH is also bonded with 2 Cls, but this RH will get 2 electrons from this Cl and 1 electron from this Cl. So you know the 2 means chlorines will have means each chlorine. So we can divide this molecule into 2 halves. So we can consider that each Cl will contribute 3 electrons in all. So you can count 2 electrons by this chlorine, 1 from this. So this chlorine means overall we can take this chlorine as a whole for here, 1 chlorine here. So in overall this electron means you can find here this chlorine contributes 2 electrons to this RH, 1 here. Similarly this Cl contributes 1 electron here, 2 electron here. So you can consider one of them. So 9 plus 4, 13 plus 3, 6, 36, 16. And so here we are having 16 electrons. So this configuration is not attaining the 18 electron rule, means it is short of 2 electrons. So the formalism shows that for electron count we have to consider each or every ligand without or irrespective of their charge. Means it may be negative or having neutral charge. It will contribute, or it is considered, means while we are taking the electron count we have to consider it as a neutral species even though it is Cl minus. Then there are, in short we can show that there are several rules. There are several rules which shows that the electron count by donors that is ligands. So here we can show that, so depending upon the number of electrons contributed, we are classifying just here the donor atoms. So first we will see 1 electron donor. So these are the hydrogens. These are the hydrogen atoms. Then terminal Cl. If the halides are terminal, then it will contribute 1 electron. Similarly Br, similarly R. Similarly we can have R. Free radicals, in short we can see RO, free radical. Here R is alkyl or phenyl. R is alkyl or phenyl. This R is alkyl or phenyl. Then second class is 2 electron donors. 2 electron donors. So there are examples such as carbonyl, carbon monoxides, then trialkyl phosphine PR3, then UR3, then R2C, then eta2R, then R2C, that is carbene. Then 3 electrons donor, 3 electron donors. So we can have the example of eta3, that is eta indicates the number of ligands, that is how many atoms are sharing the electrons with major ion, that is 3 electrons are here radicals. These are radicals. Then RC, that is carbonyl. Then mu Cl, similarly mu Br, similarly mu I, that is bridging radicals, like this. Then one more is mu R2 P. Then we can have 4 electron donors, 4 electron donor species, ligands. We can have eta4, dyne, eta4, C4R4, cyclobutyrene, cyclobutyrenes. Then 5 electron donors, these are eta5, that is CP, cyclopentadiene, mu3, bridging Cl radicals, bridging 3 Br radicals, then bridging 3 I radical, and bridging 3 mu3 Rp radical. For each of them will contribute 5 electrons. Then 6 electron donors, 6 electron donors. These are eta6. These are eta6, that is C6H6 and other eta6 rings. For example, eta6 C6H5 Me, C6H5 Me. Then the last donor is 1 electron, 1 or 3 electron donors. Now electron donors. So there is this NO nitrogen C, which is having 2 electrons and 1 electron donor like this. 1 or 3 electron donors. So in one example, it is so we can have here M example. This is example M, double bond N, double bond O. So here it contributes 2 electrons, and another example here contribution is like this. So this nitrogen contributes 1 electron here. Then if we generalize, then we can show this MXM, where X is, where this X is Cl, Br, I, Pr2. So we can have this structure of this complex eta 5 Cp or C5 C5H5, and this is Ni, Ni. So this is bridging with PH2, Ni. Here in P, PH2. So we can show this contribution like this: eta 5 C5H5. So the electron count for this is, so electron count is here in K. Valence electrons are 10. Then eta 5 C5H5 contributes 5 electrons. Then PPH2 bridging, PPH2 bridging, or in other words we can say mu, that is mu, contributes 3 electrons. So total gives us 18 electrons. So in this way we can have negative atomic number and its importance, that is importance of effective atomic number. So we will see one by one number of such examples. This is why the effective atomic number is important, because when the atom is unstable, then it tries to attain stability by combining with suitable number of ligands or other species, and thereby attains the nearest inert gas configuration or next inert gas configuration. So in order to study this, means how the every ion or atom of transition metal or other metal atoms are in need of electrons from other species. So that we'll discuss here one by one. So first of all, we will take this Zn2 plus. So this Zn has electrons, and in order to attain nearest inert gas configuration, what is nearest inert gas configuration? It is 36. So in order to attain this thing, it will require 8 more electrons. 8 more electrons required. So these 8 electrons can be obtained by combining the zinc 2 plus with ligands. So each ligand will contribute 2 electrons, and thereby, so 8 divided by 2 is 4. So it requires 4 ligands. And in order to complete this requirement, this zinc will form complex with 4 ligands, that is Zn NH3 4 2 plus. So with the formation of such complex, the zinc will satisfy its requirement of effective atomic number. Then we will see another example. Another example is cobalt 3. So another example is cobalt 3. So this cobalt 3 has 24 electrons. It has 24 electrons in CO3 plus state. As a result of this, in order to attain 36 electron, that is next neighboring gas element, that is krypton. So it will require 12 more electrons. So needs 12 electrons required to complete the nearest to attain effective atomic number, that is next inert gas configuration. As a result of this, it will require, means if we each ligand contributes 2 electrons. So if we divide this 2, so we will get 6 ligands required. So this complex, this carbon monoxide in cobalt in 3 plus state will combine with 6 ligands in order to satisfy its requirement, and it gives COCN6 3 minus, or even you can consider CONH3 3 plus. This is just one example. Then another example, we will have another example of Mn in zero oxidation state. So this will have 25 electrons, and in order to complete its octet, means in order to complete the effective atomic number or attain this next inert gas configuration, it will require 11 electrons. So out of these 11, so it is not easy to attain this electron 11 number by using the full ligands in terminal positions. So we have to consider, means 1 electron separate. So out of this 10 electrons can be contributed by 5 ligands at terminal position. Terminal positions, and 1 electron can be contributed by 1 bridging ligand. So in this way you can complete the requirement. As a result of this, this requirement can be completed by bridging. This is one option, but there is another option by formation of MN-MN bond. MN-MN bond is another option. So this option is suitable. So it will produce the compound such as Mn2CO. So 5 ligands Mn2CO5 each, but totally it will require 10. Means this can be alternatively shown as CO5 MnCO5. So that is Mn2CO10. So in this way, this Mn in zero oxidation state will form MN-MN bond, that is, it will form a binuclear complex and attain the stability showing next inert gas configuration. Cobalt is another example where cobalt is in zero oxidation state and it has 27 electrons, and it will require 8 more electrons to complete this magic number, that is 36 for krypton, that is effective atomic number. But here it will show the formation of this attaining the special stability. So there are 27 plus 8, it cannot attain 9 because it requires odd electron. So one more electron, this is added, plus one more electron from MN-MN bond, CO-CO bond. From CO-CO bond. So in this way it will complete the 36 number. So thereby it gives the CO4, 8 electrons are contributed by 4 CO. So CO4. But this species is not stable. This is unstable. So the species similar to this can be stabilized by accepting one electron. So this complex can accept one electron. So by adding one electron, it gives CO4 minus. So this ion is stable. So this anion is stable, but it can also form a bicarbonyl species, that is binuclear species, that is CO2 CO8, and this is stable. So this is stable, means it can either form this mononuclear anionic species or it can form a stable dinuclear or binuclear species. If we take the another type, that is metal clusters. Then we'll take the example of here Fe CO12 Fe3CO12. So this Fe3CO12 will contribute. This will contribute. These three will contribute. Each Fe has 27 electrons. So into 3. So this will produce the this we can consider only, we are considering here only valence electrons. Easy. So it can show it has 8 valence electrons. 8 electrons, valence electrons of Fe. So there are 3. So it gives 24. Means 3 Fes will contribute 24 electrons because each Fe has 8 valence electrons, and therefore it will also show the contribution of these 12 carbon monoxides. So that is also 24. So it gives 48 electrons, and so if we have taken 3 Fe, so if it is divided by 3 Fe, you will get 16 electrons. 16 electrons. So this cannot complete the effective atomic number requirement. Means here this Fe is short of 2 electrons to give the total 18, and therefore it requires the formation of a cluster. That is, the Fe-Fe bond requirement is necessary. So in order to add these 2 electrons, so it requires formation of Fe-Fe bonds. So there should be such 2 Fe bonds. 2 Fe-Fe bonds. So that will form a trinuclear carbonyl, that is Fe3CO12. So there are 2 such Fe-Fe bonds. One Fe-Fe bond will contribute 1 electron. So there are 2 Fe bonds. Means the structure will be like this. Fe like this. And this each Fe will have the 4 carbon monoxides like this. So the structure is like this. So the structure is not showing that each Fe has 4 terminal carbonyl groups. Now I will show the structure in this way. So this Fe will have this carbon monoxide like this. So this Fe will have 3 terminal COs, but each Fe will not have 3 terminal COs because in this way. So out of 3, 2 Fe bonds will have 2 bridging carbon monoxides, and this will produce the required number of 18 electron system. So 16 plus 2 electrons are added by, means one electron, say if we consider this Fe, one electron is contributed by this bridging CO, another electron by this bridging CO. This Fe bond, there are two Fe bonds. There are two Fe bonds. So each Fe bond will contribute one electron. This Fe bond will contribute one electron. Similarly, in case of this Fe, this electron, this bond will contribute one electron, and this bond will contribute one electron. So in this way also here can find. This will stop our discussion. So for further reading, you can refer number of other number of reference books from which you can get a variety of examples, and you can practice this calculation of effective atomic numbers. Thank you very much for watching. Please subscribe to this channel and press like button and bell icon. Thank you very much. See you next time.